All right.
Okay. My name is Mazin Hilali. I'm a senior petrophysicist with Local International in Westgonna 2 project, southern Iraq, Basra. Our meeting today will be regard to flow array sensing tool by OpenField Technology. Will be presented by Miss Virginia and Mr. Abdullah. Miss Virginia from OpenField, she's senior
Yep.
petrophysicist,
Hi.
and Mr. Abdullah is a domain champion for wireline and integrity with Oilserv in Dubai. Uh, and I like to make just quick presentation. Okay, and meantime, I will leave the mic for Dr. Mohammed if
Yep.
he want to say something.
Mhm.
Okay, Dr. Mohammed.
Yes, Mr. Mazen. Um, okay. Miss Virginie and Mr. Abdullah, welcome to you and our attendees in SPWLA Iraq chapter. Welcome to you too. This is Muhammad Jawad Zainul Abidin, Vice President of Technology at SPWLA Iraq chapter and Senior Faculty Member at Petroleum Engineering Department, College of Engineering, University of Kirkuk. SPWLA Iraq chapter today would like to present you to free webinar, the fifth webinar in 2024 in regard fast production logging system, tool theory and case studies or cases studies. Uh, Today we have two presenters. First of them, Ms. Virginie Schoepf. She is a senior petrophysicist in OpenField Technology, and she is a member of the SPE, SPWLA, and IAH. Virginie holds a MSc degree in geophysics from École de Physique de Globe de Strasbourg. And with Mr. Abdullah Maani, he is a wireline domain champion with
Mr. Abdullah
Oilserv.
Al-Mani.
نعم.
Abdullah.
He is, yes, Mr. Mazen. Mr. Abdullah is a wireline domain champion with Oilserv. He has MSc reservoir engineering degree. He got it in 2016 from the United Arab Emirates University, and he joined Oilserv in 2015 as a wireline domain champion based in HO in Dubai and covering for the Middle East and North Africa region. So we hope you have a great time during our webinar and at SPWLA chapter of Iraq. Thank you, Mr. Mazen, and Mike with you.
Okay, thank you, Dr. Mohammed. I will make very short presentation.
Yep.
So as we mentioned, this year will be mostly focused on production logging. This is webinar 5, not 4. This is the fifth one. Will be with company and combined between OpenField Technology and Oilserv. We plan to do a few extra webinar this year, as you can see in my screen with Schlumberger, Kappa, ISP, GeoActive, and TGT for this year. And I like to thank all our sponsors that support us with all these technical events. As we did last year, if somebody attend this webinar for 6 or more of these webinar will get a special certificate called Super Learner. And if you like to join our Iraq chapter, that will be our pleasure. Without further ado, okay, Virginia, you can start sharing
Here's the
and
slide.
start the slides. Thank you so
Yep.
much.
Thank you very much, both of you, for the introduction. I'm sharing the slide. You should see my screen. Can you see it?
Excuse me, Virginie, before you start, regarding the timing for the presentation, Dr. Mohammed and Mr. Mazen.
You
So
can
how long we have?
you
So we
can
can
extend
adjust.
till 90 minutes, no problem.
Yep.
All right, good enough.
That
Thanks.
give us more time. Ouais. So thank you very much, SPWLA Iraq, for inviting us. As we said, today we're going to present about the FAST, which is the commercial name of some of the production logging tools of OpenField technology. And Abdullah is going to present the case studies. So the OpenField has been around since 2011. It's a small company based in France, but the DNA is to use MEMS sensor. MEMS stands for microelectronic system, and because MEMS are really small, very small microchips, we are able to make tools that are really much smaller than existing. So we were challenged to develop an integrating production logging platform to quantify flow in deviated wells, multi-phase environments, and also complex reach. So what we came up to is to develop a very short string. It's around 1 meter long, with measurement, everything you need to calculate, to derive a flow profile. So in terms of size, it's around 3 feet versus equivalent, which can be quite long in production array logging. The bonus of this size is to have easier access, and because we have co-located sensor, we have also more accurate quantification of flow profile. There is one, we believe it's a groundbreaking measurement is a Doppler. So I have a slide on this, but we continue to have different every year, continue to have different innovation. So the agenda for today is, I think the first part myself, I think it's going to be around 20-25 minutes, and the rest of the time it's going to be Abdullah during 4 case studies is going to show you how the technology perform in the field. So that's the plan. So what does OpenField technology have as an offer, production logging offer? So we do have say a PLT family to use the commercial name as a FAST family. So FAST stands for Flow Array Sensing Tool. The first instrument that was developed was what we call the FAST V2, is around 1 meter long. That's the one here that is displayed, has is 11116 tool, around 7 kilos, has a measurement inside the tool body, so pressure, temperature, Doppler, ultrasonic ceramics, also MML measurement that is similar to CCL, inclination, relative bearing, the electronics, and also a battery sub if you want to record the data on memory. So it can be deployed in surface readout, also on slickline or memory. And even when it's recording, it's doing surface readout, people tend to acquire data in memory. You never know if you lose maybe contact with surface, and also it's always another set of data. With the memory, you've got data from running all to pull out of all. Then we have a azimuthal part of measurements that is performed using four bowspring arms that can support centralize the tool own weight. So on this V2, there are 2 local probes per arm. I will show you a better, more detailed picture of that. So typically on each arm, we are going to put one flow meter device that can be a micro spinners, and another one would be next to the spinner on the other side of the arm, very close to each other, hold up measurement. so that we can reproduce on all the arms. The important fact is that we can mix and match the type of physics on the arms. I will come back to that. So since the fast V2, that was the first tool that was developed, there was a fast V4, so similar tools with 4 arms. This time we have also measurement on the bottom arm, so we have then 4 probes per arm, 4 local probes per arm, azimuthal probes. Because we came across seam completion, there was a slimmer version of these two, 1/4 tool. So I think that's the slimmest array PL production array tool that we are aware of. So that's typically to be run in restriction less than 2 inches. And then the very new tools, the axial fast was presented, or SANS tool was presented in ADIPEC last year. There will be a case study on that, showed by Abdullah. That's this type of geometry, so it's really designed for, this tool doesn't rotate, it stands on the low side of the pipe. It's really for highly deviated wells, I would say. Then we have the sleek fast. So the sleek fast, that's it's commercial also already. The sleek fast, that's a central sonde with a single flow meter, a single helix, and array probe, similar technology of what we have on the fast. So that was driven by wells that are less challenging, less deviated, more homogeneous flow, also for intelligent drift run. And the last tool that is not yet commercial is what we call V6. It has 6 arms, so I can present you this tool, but I mean, it's not yet commercial, so I'm just mentioning it here. Well, operation-wise, we, as OpenField, we are selling or renting tools or also probes, not only tools, also we sell single probes. We, up to our best knowledge, there's been more than 330 runs globally across the world with different type of operators, different conveyance. So these dots, the color of the dot represents the conveyance. Red is tractor. Also a lot of the North Sea, also some of the US or Canada. There have been also coil tubing, of course, in horizontal wells. Some people also use coil tubing. So in China, US land, the Middle East, it's not always mentioned here as dots, but it's been deployed in the Middle East with coil tubing. Abdullah can talk about that. So on 1/3 around of this well is highly deviated, so more than 70 degrees. In different type of reservoir, conventional or unconventional. And some of the survey we are OpenField directly engaged, especially if it's the first time the tool is developed. There is a OpenField office, head office in Versailles. That's where we develop, assemble tools, develop new tech. And then there is an affiliate in Houston. So Linda Abbas is managing the American continent, and she's managing also, there is some service that is done in the US, where people can, operator can directly contract OpenField for jobs. So the business model or DNA is MEMS, microelectromechanical chips. So these are tiny mechanical systems, pressure and temperature, the size of a breadcrumb. Then we have also different physics, ultrasonic transducer, micro optics, microwave, micromechanics, and all these bricks we assemble into smart sensors. So for some of them, it's going to be, let's say, a spinner probe or a Doppler probe, microspectrometers, and we can go further up in the scale. We can assemble these different physics on tools, so production logging tool for the fast. We have also project on logging while drilling that can be machined these gauges and put into mandrels, and also more on the reservoir monitoring, some gauges too. So as I say, we are sometimes we are mostly R&D and developing tools, but we sometimes engage in supporting acquisition, especially when it's the first time the technology is introduced. So there are different type of fast. I think it's important I show you that because there is a maybe then Abdullah is going to discuss this in the case study. So the first fast tool was a fast V2. It's 3 feet long, has pressure and temperature, MEMS pressure and temperature inside the tool body. There are some Doppler ceramics inside the tool body for this version, 8 of them. Doppler around 10 megahertz of frequency. And then you have the centralizer arms that self-support the own weight of the tools. So here, for instance, we see macro spinners, the small propellers that for flow speed. And here there is a hold-up probe. It's in transparent, it's sapphire, it's the optical probe. But actually you can mix and match. You can remove these probes depending on the needs of the logging survey. And that's shown in these cross sections here where, you know, up to the client operator logging objective, we can decide to choose the best probe. For instance, if it's gas wells, we'll tend to use optical probes and spinners. Now, if it's more what oil producer with hot water holdup as main focus, we tend to use more electrical probes, whether it's conductivity or capacitance. So that's really the important is a main tool body state, and then you can change this based on the logging objective. So that these probes are these local probes that we design and that also we sell individually. And you know, as we start with the problem, what is the problem with the well? What is what are the limits? You know, whether it's ID or also flow speed limits or rates, and we decide on the type of sensors. As I said, there is also a tool that has 4 probes per arm. That's what we call the V4, and that's what we show here on the cross section. So when we have 4 probes per arms, you know, we can sometimes use only one tool. That's combining optical in yellow for gas holdup and capacitance for water holdup. So that's one of the possibility. The tools can be stacked. So this is only 1 meter, and in deviated wells, and especially horizontal well, we tend to stack the tool together. That's to guarantee that you're going to have 45-degree azimuthal sampling. So in terms of measurement specs, I know that's very tiny to read, but we will send you the you know, the slide. So there is one parameter is the inclination that is measured by the tool. Relative bearing is also built in the tool. For the gas holdup and water holdups, we are in terms of accuracy around 1%, and the resolution 1/10. So what we mean by accuracy, so absolute accuracy, is 1%, and the resolution is if we are in a stable situation, stable flow, and we compare passes together, we are you know, we are measuring repeatability around 0.1%. So it's in terms of flow speed, the macro spinner have very low threshold, below 1 meter per minute, and they can operate at very high speed. They can rotate up to 1000 RPS. So there have been survey where we have around 10, 15 meter per second. So that's really around 900 or 800 meter per minute. So times 3-4 feet per minute. So slow down a little bit, go back to what we have in terms of hold-up probes. So here I'm showing 3 main times. We have designed a bit more, but for water hold-up, there is a conductivity probes. So conductivity is a measurement is based on having 2 active electrodes, and they try to establish a circuit, and depending on what is the fluid in contact with these electrodes, let's say it's water, that the electrical circuit will be closed, and we will measure relatively high voltage. For the water to be detected, it needs to be a certain size. If it's in bubble flow, we need a bubble size of 1 to 2 millimeter, and it's related to the spacing of the electrodes. So when we stand to have a high rate, whether it's emulsion, oil emulsion, or mist flow for gas, a high gas rate, these water droplets will be below that size. They're going to be sheared, and they can easily be below 1 millimeter. And this is why we develop a capacitance probe. So the capacitance probe works similar to full bore capacitance. You have an active electrode, and we are looking at electrical charges in the vicinity of the probe. The circuit, the volume of investigation is the distance for the volume between the active electrode and the next piece of metal, so which can be the casing ground or also the tool body. If I just going back, you see, imagine the capacitance probe here, and the next piece of metal would be either the casing or actually the tool arm. So that will be a localized capacitance measurement. So as any capacitance, if in this volume there is more than 50% of water, the capacitance will be short-circuited. Actually, if we are looking at measuring very small droplets, that's the main interest of the capacitance. We are going to be able to measure water holdup. So I have a small movie about that film. Sorry, trying to see. It's quite small, but this is a probe where we measure capacitance and conductivity at the same time. And what we've done in this probe, there is oil, and we are adding a little bit of water. So there are two tracks. There is one, the electrical level, the conductivity level, so this probe. And this level will stay low if you are in gas or oil. Here, in this case, is oil. And if you, normally in water, this level should be quite high. I will replay the movie if it needs to be, but this is a track of the capacitance versus time. So during the experiment to this oil, we're adding each time 10 millimeter of salt water. And I don't know if it's clear here, but what you see on the capacitance, each time we are adding salty water, we can see a step change. So increase of capacitance means increase of water holdup. I can replay. So we're starting with oil. We can see 100% oil. We can see the probe. And as we are adding water and it's going very high in this flow loop, you start to not see the probe. That's because it starts to be like a mayonnaise, let's say. You see mostly oil and then some little water of droplets. And the electrical level, the conductivity level stay flat and low. And as we're adding water to the system, the capacitance is detecting. So that's what we see also in the field, that when we combine these two in oil emulsion, the conductivity generally or resistivity probe, similar to similar problem, will not detect the water in oil emission. Another type of probe that is very much deployed, the optical probe, especially if you have gas. So the optical probe is based on measuring the apparent refractive index of light. There are two fiber optics in the sapphire probe. One is shooting light toward the end of the probe, and through, depending on the fluid that is in contact with the sapphire probe, there will be a certain angles of reflection inside the probe. If there is gas or air, most of the light is reflected inside the probe and measured by the photoelectric detector. If you have oil, a substantial part of the light is going to leave the probe. This is how we can distinguish liquid from gas. And actually in good condition, we can also make difference water versus oil. I mentioned the micro spinner. This is more in zoom what we have. So there are two main models. Mostly we use client ask for 11 millimeter OD spinner. So really they are the half an inch spinner, these ones. There are different types of material. Essentially we install hard plastic, which can be PEEK or POM. PEEK are this one, POM are also dark, and even there have been some titanium order. That's for very special occasions. So the PEEK and the POM, they can withstand 15 millimeter per second. So that's higher even than 60 megascaf a day of gas rate, if we're speaking about rate, or above 50,000 barrels a day if we are talking about liquid. So there are slightly larger spinner that were more deployed to try to see if we can decrease the threshold. So the threshold of the spinner here in feet per meter is quite low already for 11 millimeter. There is a bit of decrease of using the larger blades. The slope is very similar between the bigger ones and the small ones. It's rotate quite easily. So slightly lower threshold for the 20 to 19 millimeters. So advantages of this tool versus conventional PL has been illustrated in these papers. There was a customer that was using mostly conventional and in wells that were not so deviated, that can be 30 degrees, 40 degrees. They were using conventional in kind of two types of wells. One type was really with very high water cut above 90 degrees, with sometimes three phases being produced, like in this example, where we have two main set of perforation, two main reservoir units, P2 at the bottom and P1, and they're trying to find out if they can shut off the bottom part. For that, in 90% water cut, they didn't manage to have an accurate view with a conventional sensor, but they deploy the FAST, the OpenField tools, and they repeat, they did several passes, and they reliably measure water holdup, oil holdup, gas holdup. And here it's hard to see, but we are really zooming into 90%, around 90% of water holdup, or 10% or 5% of oil and gas holdup. And they're really exaggerated scale. And with the result that that repeatedly they could see that definitively there was no hydrocarbon being produced at the bottom, and P2, and that's really challenging the accuracy of 1% and having a repeatability of the phase holdup below 1%, so around 0.1%. So that was quite stable well, so they managed that, and they were able to say that only water is being produced by P2, and hence they set a plug between the two reservoir units and increase the hydrocarbon production. Another case that they explain is when they have a low rate producer and around 7-inch casing, so quite large borehole, maybe around 1,000 barrel liquid a day. Here it's an example of a gas producing well where sometimes the water cannot be lifted anymore. So the water is blue, gas is in red. So what's going on in this well? They were even not measuring the total rate correctly by per depth, because the spinner, the full bore spinner, sometimes reading 0 APS, reading 0 velocity, depending on where it was standing versus depth, or even negative. Because if you have a large fraction of the section that is reading occupied by water and water's going downwards, your spinner can read a negative velocity. So then by having array tools, so hold up and macro spinner, they were able to decouple the hydrocarbon versus the water flow. And that was again a customer that was really didn't want to spend too much money with PLT, but at the end was demonstrated, the service company demonstrating that only with spending deploying an RAPL, you could really manage your reservoir. There is one wanted to introduce to show some example of a fast also in a horizontal situation. So that's an example of a horizontal oil producer with high GOR. It's a choke reservoir fracture with a sliding sleeve. So that's in the red, that's where you have the entries, and the sleeves you can close. The inclination is above 90 degrees. Inclination here. Water holdup E is water holdup from the conductivity probes. So here, all these three maps: water holdup, gas holdup in red and white, spinner in red and blue. The nomenclature, the convention is that the middle is the high side. So the high side is in the middle, so it means that you have a light phase here in with zero water holdup. It can be gas or oil. So the yellow stands for hydrocarbons. It's on the high side. Then if we look more in detail, thanks to the optical probes, we can differentiate gas versus liquid. So now the optical probe is giving us the gas holdup, and we can see, compare the area of gas holdup versus total area of hydrocarbons, and we can see that most of the hydrocarbon actually is gas. So also gas is on the high side. And then the spinner data, the RA spinner, is showing something interesting here. There is a difference when we are at the bottom half of the well. We can see blue is lower IPS, or lower apparent velocity on the high side. And when we go towards surface on the upper part of the reservoir, we can see there is a change, a flip, that now we have higher velocity on the high side. So why is that? That we are crossing where we have the dotted line inclination. Below that depth, we have higher than 90 degrees. So if we have higher than 90 degrees, it's like we're going down downwards a bit towards surface. So water is on the low side, and water on the side, you have the low side. Water is going much faster than the hydrocarbons. When we are below, when the inclination is below 90 degrees, now we still have, of course, hydrocarbon on the high side, but this time the hydrocarbon below 90 degrees deviation will go faster than the water on the low side, and hydrocarbon on the high side. So in this case, hydrocarbons are slipping over water. And that's why, again, you need RAPL. A conventional PL is not able to measure the flow speed reliably. Why?
Just a
Yeah,
question,
yeah.
quick one.
Yeah,
So
yeah.
the yellow and the WH, the yellow, sorry,
Yeah.
yes,
Yeah,
the yellow is
yeah.
is hydrocarbon? This
Yeah,
is the gas?
the yellow is, thank you, Mazin, for facilitating. This map, WHE, the water holdup from the conductivity probes. So the color bar starts at 0 here. 0 is 0% water, and it means hydrocarbons. 1 is 100% water. So blue color is 100% water. And so the yellow, it can be gas or oil. The conductivity probe doesn't distinguish oil from gas.
Okay, thank you.
And this one, thank you, Mazin, this one is a gas holdup, GHO, gas holdup from optical. 0 white is no gas. Red is 100% gas. So when we compare the surface area, and of course we can do that, that's an emerald plot, YW is the average water holdup from this map. So for people who are not familiar, holdup, emerald is calculating an average depth by depth. So if it's deviated, it's going to use a layered model to produce the average of the water holdup. So here you see, for instance, very low water holdup, a lot of yellow. YG is the average water holdup using the MPT module of emerald, and that is the average for each depth. And you can see here YG is 85 or 90%, which means that most of this hydrocarbon is actually gas. Then we go to QZT. So what is QZT? Is a cumulative flow profile. So that's the blue shade is a cumulative water being produced. So you can see that they didn't manage to go completely reaching the last producing interval. So we start here and we can see from the bottom we are producing mostly water, but there is some hydrocarbon. And then at each sleeve, there is not exactly each sleeve, but there are sleeves where we can notice quite big inflows. And most of here we are produce hydrocarbon. And you see the water is not increasing very much. The water increases again here and here, but unfortunately water production increases at the same time as hydrocarbons. So that's often the case in, I think, in fracture reservoirs, that you have mixed water and hydrocarbon. That's make the water shut-off complicated. And that this track is the view versus TVD of the cross-section of the well, so the face occupation. So that's more or less using these two curves, YW and YG, and okay, oil is 1 minus YW, YG, and then you can see, you stack this, it's cumulative view of the holdup, more water at the bottom, and then you see a lot of hydrocarbons, and then again more water. And how do they manage this water shut off here? They couldn't shut off completely the water because they don't want to condemn this, so they put a plug toward the bottom, and they also inject some chemicals here to change the relative permeability of water. So that's will plug reduce some water, but not all the water. A last example before I introduce the axial fast or sense. I wanted to, because that's a question that sometime came up. Why do we need to stack two tools? There are some people that want redundancy. Our tools, they rotate quite well, I would say below 70 degrees. But when we are tractoring, like here at 90-degree inclination or more, the tool doesn't rotate so much. So if you have only one tool and you are maybe in a big borehole and you are trying to chase 10% of gas holdup, of oil holdup, or water holdup, it's better to stack two tools. And if we look now in cross section, you will have an arm every 45 degrees. And this example was a producer, another high GOR oil producer with two fast tools being stacked. There was 3 up and down passes. These are, I'm just showing here a gas holdup map. So each track here is a gas holdup map related to one pass and one tool. T1, this tool, is the one with the arm at 0 relative bearing, so looking vertical. And the probes is really at 10 centimeters from the entry, so really close. And this tool was able to detect a very low fraction of gas. And that's why you still see gas here in the middle of the track, that shows a high side. The other tool was 45 degrees shifted. So this tool doesn't have a probe very high. So when we go and when we look at the top section, the 3 up and down passes of the tool T2 and T1, they look quite similar. But actually, if we look at the bottom part, we are not seeing the very low gas holdup. So this is really segregated flow. I mean, what the image show that there is very good repeatability between passes. Thanks to two things: thanks to well being quite stable, and number two, thanks to the quality of the optical probes. So that, and this track here is by when I combine the two tools, I have a better resolution, resolution of the holdups. The tool has been benchmarked with FSI. FSI is a SLB tool that is an old paper 2018. In oil producer, FAST was combined with FSI in a quite small ID. There's been good agreement between FAST and FSI. I don't want to go in all the details, but what the analyst log interpreter did at that time, they compare the water drop from the FAST with the FSI in green, with the FAST in pink, the oil rate, and then also the water rate. So they are very close, and that operator decided to use more the FAST. One another most recent example. There are not so many published example of comparison because it's quite rare to compare different tools from different vendors. So that's FSI versus FAST. In that case, that was published by recently by Dong, 2023. This is tight gas, and what they found is the FAST could reach a longer interval, could reach further down the well, and there was also better repeatability of hold up. So on this side, we have hold up of FSI, hold up of FAST. Different colors mean different passes, and here on this side we have a velocity, so different spinner from FSI and different spinner from FAST. From FAST, I think they only use one tool because this is quite small boreholes, 4 inches, and yeah, they don't feel the need to stack the two FAST, and so that was their findings. We were not a co-author of that on OpenField, so but we wanted to note to show this more recent publication exists. In terms of measurement, I'd like to also speak about the Doppler. So what is the Doppler measurement? The Doppler is a non-contact acoustic flow meter. We have Doppler sensor inside tool body for V2 FAST, and also as array probes. So an array probes will be added just like a spinner or holder probes on the arm of the tool. Benefit of array versus body Doppler is that we can be closer to the perforation or the reservoir, and we can put array Doppler across the circumference. So we have deployed now this in a lot of wells. The more recent progress is that these were recording the frequency spectrum, and we are able to have very good comparison to spinners. So spinners, we are not measuring exactly the same thing, but what we are measuring with the Doppler, we're shooting some ultrasonic waves, and if from the transmitter emits and also receives, so it's a transceivers. And if we are in the presence of heterogeneity in the flow, can be bubbles or sand grains, this heterogeneity will propagate backscatter back the energy of this wave to the transducer, so transceiver. So there is a comparison of frequency that is emitted versus what you get back. That's done real time using a fast Fourier transform. So what we are measuring exactly, we are measuring frequency shift, frequency difference, not measuring a velocity. But if we use a Doppler equation and also passes at different speed, we are able to calculate, convert, I would say, frequency shift into a speed in feet per minute. So that being done, deployed also in environments such as this, when we have the tool covered with a lot of sticky mud. I don't remember if I have some animation. Should have, but sorry, no, it's not working. But we have I have here in this tool 4 array probes, and each probe has its own frequency spectrum. So this is versus depth, and this area is a frequency of the Doppler. So when we have a larger frequency, that means higher speed. So there are 4 probes. Not all 4 probes reach the same frequency or apparent velocity. If we put this frequency, extract this frequency shift that can be done automatically, we are able to, if we have 4 probes, we're able to do a map And here the red is high frequency, the blue is low frequency, and again the middle is on the high side. So what we see, we were seeing a distinction of speed between high side and low side. They were run in a well with high water cut, but there was on two phases. There was oil and water, so we could were able to measure speed in this well, and to even notice you know, difference of speed between hydrocarbon and water. That is again expected. The mini spinner in this environment, the sticky stuff were close to the wall, so the mini spinner after some a while start not to rotate anymore. So we were really happy to have continuous data, I would say, with the Doppler. Well, I will just mention the slick zone that it's not for, I would say, not for highly horizontal complex flow, but has a works well, I think, in low deviation and in also maybe in dummy runs. So it's half a meter, a single helix in a cage, and then you have these probes that are similar to other the fast showing different physics, conductivity, capacitance, optical resistivity. So it will not replace fast array tools, whatever array tools, if you have water recirculation, liquid recirculation, but in places where maybe you don't have recirculation, but you are looking at small percentage of hydrocarbon, that could be used. On the SANS tool, I'm close to pass the baton to Abdullah with the case studies. So the SANS was introduced in ADIPEC. It was developed with the help of Oilserv, who sponsors the development of the tool. And so Oilserv has deployed many times in the Middle East. The outside the region where Oilserv operates, this tool is available without, you know, Oilserv deploying, but in the Middle East, I think Oilserv has exclusivity. So that's the tool is similar, has axial geometry, sits on the low side, and has a lot of sensors. It's 2 meters long, can open to 9 inches to 1/8 of diameter, and on each arm you can have 2 type of probes. Similar to the other tools, we can mix and match the type of sensors. And at the back arm, you also have levels with each time 2 probes. It's pantograph mechanical system, so which means that when you close the tools or deploy the tool, these probes, they will stay in a horizontal plane. It's not going to be tilted, you know, parallel to this arm. The probe axis will stay horizontal. There will also be probes at the bottom, pressure, temperature, 1D caliper, and then in terms of probes, you can put different physics. The tool was introduced last year in ADIPEC. ADNOC was the main author of this paper, and Abdullah is going to show you the case study. So Abdullah, I don't know if you want to share or you want me to continue flipping slides. Are there any questions on my part?
I believe it's better to share from my side, Virginie.
Yeah, okay.
So I can control.
Yeah. Sorry, it's lasted quite long, but yeah.
What?
Right.
Where's your mother? I don't know. Wow. Well, apparently she's in a taxi on his way over to Keighley.
There's
she's
some
giving
acoustic. Hello?
All right. Can everybody see my screen?
Yep.
All right. So any questions for Ms. Virginie before we start with my part? All right. So I believe it's better to give some time at the end of the presentation for question and answers. So in this part of the presentation, I will present the case studies. And as Virginie said, we have 4 case studies. Let me just activate my ledger point, please. Okay. All right. So the first case study will show the benefit of FAST or CFA. We call this tool in Oilserv as CFA, Complex Flow Analysis Tool. It will show the benefit of this tool compared to the conventional production logging and deviated wells. And then the second example represent a benchmarking with the existing array tool. Here we are talking about maps. And then the third one is basically a comparison with the MPLT or PLT, conventional PLT at high gas-oil ratio. And here we'll show you the benefit of having Doppler measurements. And finally, we'll present the new technology, which is Sense tool. This is the axial tool. And we'll show you an example where this tool was deployed in a hostile environment, horizontal well in Abu Dhabi. So for the first case study, we have highly deviated one. Maximum deviation is 87 degrees. So this one is 8.5-inch open hole with 5.5 liner. And this liner is equipped with SSDs. So the open hole is divided into, I think, 10 compartments, and each compartment has SSD where the production occurs. So the objectives of logging here is to define the production profile and to identify the water entry points, since this well is producing oil and water. So what we run here is the conventional PLT with the full bore spinner, inline spinner, capacitance, density, XY caliber. Then we have pressure, temperature, and so on, the accessories of PLT. And at the top here, we have dual fast tools. And each fast, the first one consists of 4 spinners and 4 optical probes, the triphasic optical probes. And the second fast contains 4 spinners and 4 capacitance, right? So this is the spinner data. From left to right, we have gamma ray here, and then we have the MML or CCL from fast tool. This is the well diagram with the SSDs here. These marks are the SSDs. Then we have ILS from PLT, PLT full bore spinner. And these 8 spinners are the dual fast spinners. So each tool has 4 spinners. And in total, we have 8 spinners. This is the cable speed. So we have started with the calibration passes at the top of the top SSDs. And then we have done 2 down passes and 2 up passes across the entire interval. So in general, we can see that we have good spinner data from fast. All the 8 spinners worked fine. Full bore spinner, unfortunately, didn't work. Debris or sticky materials. Inline spinner respond well across this part, and then at this point here, it didn't spin. It's reading almost 0, and this is because of the water recirculation. As you will see later on the holdup, we'll see the water holdup start at this SSD. So fast spinners are reliable and can be used for interpretation. So comparing the fast spinner data with the holdup, here we have the acoustic density data from PLT. And this is the water holdup, oil holdup, and gas holdup from the optical and capacitance probes of fast. So we have a good agreement between the density and the probes data. You can see at the bottom here below this SSD, the bottom SSD, we have water, stagnant water, as shown on the well trajectory here. Green is oil and blue is water. And then we have oil, clean oil, there is no water. and this is clear from the density readings and from the probes data. There is no gas across the entire interval. And at this point, from this SST in the middle here, we can see some water. And you can see the increase in density, increase in water holdup, decrease in oil holdup. And this is the first water entry into the wellbore. And that's why at this point here, you see that the deviation is less than 90. Well trajectory is picking upward, slanted upward. So this place where we expect to have water circulation, and that's why at this point here, the inline spinner almost reading 0, okay, because of water circulation. So using this data, holdup data and spinner data, the interpretation has been determined, or the flow profile has been determined successfully. You can see here, this is the flow profile. Green is oil and blue is water. This is the inflow contribution or zonal contribution from each SSDs. This is the velocity match from the inline spinner. Red color or pink is the major data. Green is the theoretical output or the reconstructed data by the solver for this solution. And it's the same for oil velocity from fast, water velocity from fast. This is the well trajectory with the holdup profile. This is the water holdup from fast, oil holdup, density, and this is the temperature profile. So what we can see in the profile here is that we have oil production from the bottom. There is no water. And then we have the first water entry. And the major oil and water entry occurs across the top SSDs, which is clear from the sharp increase in velocity, all of the measurements, the BLT and the fast. And also from the temperature, you can see this profile is in good agreement with the temperature profile across most of the entry points. Now you can see with the inline spinner velocity, because of the recirculation, the estimated velocity from the inline spinner is almost 0 across this part here. So if we run only BLT here, we'll not be able actually to define the water and oil entry across these 4 SSDs because of the water circulation effect. The second example or case study is another horizontal one. And here the objective is to define as well the water entry. This is a horizontal well, 6-inch open hole with 4.5-inch liner. And this liner is completed with SSDs for this 9 compartment across the horizontal open hole section. So in this one, we have run maps and dual fast. So in the bottom here, we have 2 fast, and then we have the MAPS resistivity array, spinner array tool. We didn't run capacitance here because it is known that there is no gas at downhole conditions, so we have only oil and water. So there was no need to run the capacitance tool. Resistivity will be enough for maps. And also with the dual fast, we have 4 spinners on each tool. And we have 2 optical and 2 electrical on each fast tool. So we have total of 4 optical, triphasic optical probes and 4 electrical probes. This one is known with an emulsion flow. So the water and oil flow as an emulsion flow, as a well-mixed single phase flow profile or flow regime. You will see later on the holdup. However, here we compare the MAVS spinners data on the left here. We have 6 spinners with the fast spinner data we have 7 spinners here. One of them didn't work. However, we have 7 worked fine. And in the middle here is the temperature data, temperature profile. So we can say that we have good agreement between the MAVS and CFA. You can see both tools are showing almost an identical spinner velocity profile with the major contributions from this SSD. Second is here, and the third is here. So we have good agreement in terms of the spinner measurement. Okay. For the measurement, this is the resistivity probes. We have 12 probes in RAT tool maps. So this is the resistivity data, and this is the hold-up image for the resistivity tool. And these are the water hold-up measured by the triphasic optical probes from the FAST tool. Right, so we have 4 probes of optical, 2 down passes, green and blue here, and this is the hold-up image from the optical probes. So what happened here, if you compare the data, water hold-up, you know that resistivity probes in MAVS, they are reading about 0.5 if it is water, 1 if it is oil. So below this depth, these 12 probes are showing kind of mixture of oil and water, which is the case with the fast optical probes. And if you look at the image, you can see on the edge here, which represent the lower side of the wellbore, we have water. In the middle, it is oil. And you can conclude that the flow regime up to this point is a stratified flow regime, where the water is moving on the lower side, oil on the upper side of the wellbore. And there is a good agreement between the resistivity probes and the optical probes. However, above this point, which is a major entry as per the spinner, the water holdup from the resistivity probes has disappeared. It shows only oil, whilst the water holdup is measured properly by the optical probes across the entire interval. And you can see sharp increase in water across this point and at this point across this SSD number 3. So why the holdup disappeared, water holdup disappeared here? It's because of the emulsion flow, because of the high speed here of the entry from the middle. The flow regime has changed from stratified flow into emulsion flow. And because the water holdup is much lower than oil, so the fluid is oil dominant. And in this case, it is non-conductive, and that's what is measured by the resistivity probe. So it's either showing either conductive or non-conductive. And since the emulsion is mainly the dominant here is oil, that means the mixture is non-conductive, and that's why the resistivity probes has missed the water holdup across this interval where we have an emulsion flow. So using the MAVS data, the water holdup measured by the resistivity is really underestimating the water production or the water cut. And you can see with the MAVS flow profile, only 2.5% of the water cut was estimated, compared to 15% that was produced at surface. And with the CFA or FAST tool, we have managed to calculate or to estimate about 15% or 16% of water cut produced during the job, which is very close to the surface measurement. And you can see in terms of water velocity, oil velocity, red is from MAVS and green is from FAST. We have good agreement in both measurements. However, for water holdup, you can see that the triphasic optical probes has estimated or measured the accurate water holdup that was translated into an accurate water production, whilst the resistivity probes has underestimated the water holdup, which result in estimating very low water production compared to what was produced at surface during the survey. All right, so these are the two entry points, major entry points of water that has been well determined by the CFA data, especially the triphasic optical probes. Moving to the third example, which is CFA versus PLT in high gas oil ratio. And here is another horizontal well. Same completion almost, open hole with 4.5 inch liner that's equipped with SSDs. And here we run BLT, a conventional one, with one fast tool that was equipped with triphasic optical probes and spinners. So in this example, as you can see, the main objective was to identify the water and gas entry points, since this well is oil producer with high gas oil ratio. And this is the spinner data from PLT, the full bore spinner. And these are the 4 spinners from FAST. This is the trajectory with the holdup profile. As you can see here, the water holdup from the optical probes, oil holdup and gas holdup. This is the density from PLT and the full bore capacitance from PLT. In general, we have good agreement in terms of holdup between PLT and FAST. Similarly, we have also good agreement between the full bore spinner and the fast spinners. However, both of them, they struggle to spin across this zone, most likely because of asphaltene deposition. You can see we have poor data quality in both PLT and fast spinners. So with this data quality, we had to review the Doppler velocity to make sure that we don't have significant entry that could be missed by the spinner across this zone where the spinners have been affected by the downhole condition. So we have reviewed the Doppler frequency shift from the body ceramic Doppler transducers. And these are the Doppler data, 7 of them or 6 of them. And here are the spinner data from FAST. This is the image for the spinner image. Blue is low velocity, red is high velocity. And this is the Doppler image. Same, blue is low velocity, red is high velocity. And you can see that there is a very good agreement between the Doppler velocity and the spinner velocity, and Doppler confirmed that there is no significant frequency shift here. That means there is no significant change in velocity across this zone. And we have a really good agreement between spinner and Doppler. So this confirmed that in case of a very bad downhole condition, and you don't have spinner data, because it happened many times that you have sticky material, you have debris that can clog the spinners easily. It means that the Doppler data can be used, if not to quantify the flow profile, at least to have a good qualitative result that show you the major entry points across the load interval.
Yeah, dear Abdullah, quick one.
Yes,
what
sir.
Is what was the threshold for this? Do you remember?
For what?
Doppler, are there any threshold like minimum velocity to start sense?
It is It is hard actually to estimate the threshold. Maybe Virginie can answer this question better than me, because she has done a lot of experiments with Doppler. But in fact, it is not only the threshold that can affect the Doppler measurement, Mazen. There are many other factors that can help to have better Doppler data, high resolution data, rather than the threshold. Please, Virginie, if you want to comment here.
Yeah, quickly. Bon, these were made. This measurement were with body Doppler, so the body Dopplers are inside the tool body. Now the threshold or the smallest speed that a Doppler can measure, it depends on the acquisition parameter. So with a Doppler, we can change the maximum speed or minimum speed that the Doppler can measure. So for instance, if with some people actually in the South America have reduced the maximum speed because they want to measure very low flow. And so we need to change, if we are looking for low flow, we need to change the maximum frequency, because maximum frequency is related to maximum speed. And if we change, if we reduce this maximum frequency, the smaller speed we can measure is relative to the frequency bin. So we have around 32 frequency channels currently, and if let's say we want to have 1 meter a minute granular resolution, we need to set up the max speed for 30 meter minute. And in this present survey, if I remember, the maximum frequency was quite high, so that's why maybe we don't see really low flow, because we are setting up the maximum frequency quite high. So we can change that. And also you can change the type of Doppler ceramic. Instead of using the Dopplers that are inside the tool body, we can use Doppler probes, just like Doppler spinners, that will be set on the azimuthal arms. And then it's also we have better signal to noise, because we are directly exposed, I would say, to the heterogeneity, and we can have Doppler probes on any part of the circumference. So I think, yeah, it's if we are looking to use Doppler, it's better to use azimuthal Doppler probes, and also when you are in the logging planning, to communicate well what is going to be the speed you want to measure. I don't know if I confuse people here, but
No, it's clear. Okay, and people can maybe rewatch the recording again. Yeah, for me, like I've been interact with this one. So in general, just people to understand this one. So you have two type of Doppler, one in the body and one is as a probe, like a dedicated probe for the Doppler.
Correct. Correct.
Yeah. Okay. Sorry to interrupt.
No problem.
Continue. Yes.
Yeah. So thanks, Virginie. Thanks, Mazen. So as Virginie said, the probe Doppler can be more sensitive than the body ceramic. However, if you can see here with the spinner data, there is drop in spinner data. It's very minor. Okay, and it is still visible. So these Doppler are still sensitive enough to see the minor change in a spinner here, which represent few meter per minute change in velocity, and you can see drop in the frequency in most of these Doppler. So in general, it is this sensitivity can be increased with using the probes rather than the body built-in ceramic. Yeah.
But they are performing. I agree with you. It's a very good performance of the body ceramic in this case study.
All right. So using the PLT and fast data, spinners and hold-up data, we have managed to identify the flow profile, the three-phase flow profile. Blue is water, green is oil, and red is gas. And the gas entry point was identified successfully across the top SSD, which make it easier for the operator to shut off this gas by closing the top SSD. You can see the match across all of these measurements is satisfactory. We have good match, which implies high confidence in the proposed solution. Yeah. So that was the last example for the fast tool. Now let's move. I know that we are running out of time. Let's move to talk about the hostile environment and the new technology. As you know, most of the array tools are designed as radial arrangement.
Yeah, actually, Abdullah, you have 45 minutes.
We still have 45.
Up to you. Like we usually close in 1 hour, but if you want to extend, we have 45.
Okay. So let me go in detail for this example. It's fine. Thanks, Mazen. You know that most of the array tools, they are designed as a radial configuration where the sensors are built in kind of centralizer that will be azimuthally distributed across the whole circumference, the whole board circumference. And these tools work fine wherever you have an optimal downhole condition. You have good downhole condition, then these tools will work fine. The issue will be if you have hostile downhole condition, if you have debris, sticky materials that usually settle on the lower side of the wellbore. And now these tools are free to rotate, okay? And whenever it rotates, then you are exposing all the sensors to be on the lower side. And whenever the tool rotates, the sensors will pass by the lower side of the wellbore. They will be exposed to the hostile condition, and it will be easy to damage these probes. I can see here, these are the some of the probes damaged because of downhole condition, presence of debris, or you can clog the spinner, the mini spinners, or even the full bore spinner because of the presence of debris. So as you can see in this example, luckily the tool didn't rotate. It kept almost the same relative bearing across the entire operation or survey. And here, only the middle spinner, which was on the upper side of the wellbore, has survived. We have good data from the spinner. The rest on the lower side didn't spin because they are on the bad part of the wellbore, which is the lower side. So if this tool rotate even once or twice, then we might have clogged these spinners, and we might end up with no spinner data. And if there is no spinner data, then there is no valid interpretation that can be done, okay, even if you have good hold of data. So because of that, Oilserv, with the cooperation with in a cooperation with OPENFIELD, we have decided to develop the new technology to be designed as to be deployed axially. Okay, so it has an axial design where this arm will be collapsed when running hole and tubing. Once you are inside the casing or open hole, this arm will open across the vertical axis of the pipe. So inside the wellbore, tool will have this position. This is the lower side of the wellbore with the tool body, and this is the upper side of the wellbore, and this is the top side of the tool. So the sensors are distributed across the vertical axis of the pipe. This is similar to the FSI design of Schlumberger. That's proved to be the best design for horizontal open hole wells. Okay, so this tool is 218 OD, and it was designed to be heavy body part to keep the tool on the lower side while maintaining this arm across the vertical axis of the pipe. This frame works as a platform that can be equipped with 24 interchangeable sensors. So we have 10 sensors on the front arm, 10 on the back arm, and another 4 sensors on the tool body. So a total of 24 sensors that can be run in a single run. These are interchangeable. You can customize the sensors, what type of sensors you want to run based on the logging objectives. And these sensors can be velocity probes, like spinners, Doppler, and noise measurement as well. And it can be also all the probes, including electrical or resistivity probes, capacitance, triphasic optical probes, also, in addition to these 24 probes, the tool can measure pressure, temperature, in fact, 2 sensors for borehole temperature, CCL, relative bearing, inclination, and caliber. So you have basically all the measurements that you need for any type of flow profile, deviated or horizontal walls, in a very compact design of 2 meters in length. Okay. This is a real picture of the tool photo. You can see in the front arm here we have spinners, and we have a new technology of capacitance probes. And these capacitance, they measure the water hole depth from bottom to top. It provides 100% coverage. So if you can see, this probe will measure the water hole depth from the bottom here till the top, and the top of this probe end where the bottom of the second level starts. So you don't have gap between the sensors. So with the conventional probes, where you have space, for example, if you have one probe here and another probe here, there is about 1 inch gap between the 2 points of this probe tip, right? And if the water level in between, this probe on the bottom will see water and this will see hydrocarbon, but you don't know exactly at what level between these two probes the water level is. With this new technology of capacitance that covered the wellbore vertical direction or vertical axis 100%, it will give you full coverage for the water hole depth across the vertical axis of the pipe. And this is for the first time in production logging for horizontal wells. So the space between the two arms here is empty. And this helps actually to keep the sensors clean wherever the tool pass by strong entry. If you have debris sticking here around the probes, the entry points, strong entry points, will clean this area because it is empty. There is no metal in between that will resist the flow actually. And with this design actually, it helps to keep the sensors clean most of the logging survey. So this tool was deployed in ADNOC in Abu Dhabi in horizontal well. It is a pilot well with high gas oil ratio. And this well is a horizontal 6-inch open hole equipped with 4.5-inch liner, and these liners contains an inflow control valve to control the gas production. So these valves are designed to reduce the gas entry and increase the water entry. So it's a new technology in completion. And the objective was to assess or evaluate this completion. It was a pilot well with this completion. And this well, unfortunately, is known with asphaltene deposition. So it was expected to see a lot of asphaltene at downhole condition. And the beginning, the plan was to run maps tool, and this is the maps run. And here we have gamma ray, CCL. This is the whole diagram. And these are the 6 maps spinners. Here is the temperature, pressure, and cable speed. Unfortunately, while running whole, only 3 spinners have survived. We did calibration passes across short interval here, both the top SSD or top ICV. And then as soon as we start the first down pass, all of these spinners stopped spinning, unfortunately, because of the asphaltene. And you know, as we said earlier, that these type of tools are radially distributed. All the sensors are close to the casing wall, so it is easy to get these sensors, spinners, and hold the probes clogged with the asphaltene while running whole. So unfortunately, with this run, we did a couple of down passes, and there was no success. There was no spinner data. The most valuable data that we got is the temperature profile that indicate all the ICVs are active, maybe except that top one here, because there is no temperature deflection. So we pulled out of whole, and the client has requested to rerun with the new technology, Sense tool. Okay, so this is the tool pictures at surface after pulling out of whole, and you can see the amount of asphaltene that was sticking with the tool. So the spinners are fully covered with this hard, thick black material, and that's why none of them has spin inside the casing. So we rerun with the new tool, and this is the data from the Sense tool. We have 6 spinners, bottom spinner, and this is the top spinner, and these are the spinner in between. While running whole, 4 of these spinners survived. The middle one, the bottom one, and the top one, they stopped rotating while running whole. And that's why that's because these 2 spinners are very close. The bottom one and the top one are very close to the casing wall or the tubing wall. So they got a lot of asphaltene while running whole, and they were clogged. Okay, so we did calibration passes across short interval at the top here, about 3 down passes where these 4 spinners worked fine. And then we start the first down pass, which is the pink one here. And again, we have seen these spinners stop spinning while moving down until we reach the TD. And while pulling out of whole, you can see during this up pass, the blue color here, we can see that these spinners start waking up. So 1, 2, 3, 4, and it turned out that later on, after the interpretations, that this ICV represent the major entry point. So we have very strong entry from this ICV, and that strong entry has helped to clean the tool or the sensors because of the unique design of the tool with the empty space between the 2 sides of the arm. It was possible that the sensor got cleaned, mainly the spinners here, with the strong entry from this ICV. And we did this up pass in blue color. We did another down pass in red, and the data was monitored real time. So we did the interpretation real time and found that these 2 passes are enough with the calibration passes to do the interpretation, and then we pulled out of whole. Okay, so this is the spinner calibration across the calibration passes here. You can see the down and up passes for the 4 middle spinners. The calibration line pass through these spinner points of down and up, which indicates that we have good spinner quality. Of course, for the top spinner, during the calibration, it didn't work. We have only one point here, which is the blue color here, and the same slope and threshold that was obtained for the next level spinners adjacent to the top one was used to calibrate the spinner using these two passes, right? So using the sense data, spinner and holdup, the flow profile has been determined successfully. And you can see here, the green is oil and the red is gas. And this is the zonal contribution. Here is the oil holdup, gas holdup, oil velocity, gas velocity, and this is the water velocity from the pulse neutron tool. Oxygen activation that confirmed that there is no water movement, so the well was not producing water during the survey. This is the holdup profile along the well trajectory. And then we have temperature, pressure, and this is the saturation evaluation from the pulse neutron tools. Blue, sorry, the blue here is the water, green is oil, and gas in red color here. So if we compare the gas and 3 points, we have good agreement between the sense result or the flow profile, where it shows that majority of gas production is in the middle and the bottom part of the wellbore, which is in line with the saturation profile, where gas saturation appears on the bottom part and the middle part. There is no gas at the top, and also there is no gas production, which is confirmed by the sense data across the top ICVs. It is also in good agreement with the temperature profile that you can see. We have step change in temperature across all of these ICVs except the top one. And here, sense confirmed that no significant production from the top ICVs. Again, we have good agreement between the major data in pink color and the reconstructed data or the theoretical output in green for all of these measurements. And that indicates we have high confidence on the proposed solution. And here is the tool picture post-job after pulling out of oil. And you can see it is full of aspartame. It is really in bad condition. However, we believe that the tool got this bad condition while pulling out of hole in shut-in condition. If inside the casing, for sure the tool was much better condition than this. Otherwise, we'll have no spinner data. Okay, so while pulling out of hole, shut-in condition, the aspartame has accumulated on the tool and it reached surface in this way. Yeah, I think this is the last slide from my side. Thank you very much, and we'll be happy to answer your question. If you have question, please.
Hello? Hello?
Hello?
Yes, my voice is clear. So I like to thank you, Abdullah and Virginia, for this, let's say, advanced topics webinar. Was really
Thank
good.
you.
One of the best.
Thank you much.
All this year. If anybody have any question, he can write in the chat box, or he can also open the mic. Okay. There is a very long question. You can see the chat box, Virginia, Abdullah.
Let me exit this one and show.
It keeps on rotating.
Where is
a
it?
lot.
Chat box, it's somewhere.
Yeah,
see the
but
chat.
if you can maybe read the question, because on my side I have problem to I don't know why something is
Open
rotating
chat
all the time.
expression.
No.
Say accept. Say accept. Try to say accept. Accept.
Okay, All right.
Yeah.
Anyway, but
Yes.
maybe it's quicker. I don't know if Abdullah, if you can read the question, or the person who has question can
Who's this? The guy?
summarize the question. Yeah.
Stephen, this is from Stephen.
Yeah.
Stephen, can you?
Yes. Can you guys hear me okay?
Yes.
Yes.
Yeah, sorry for the long question. I had to give it context. For Virginie, my question is, do you have any examples, or are there examples where your sensors don't agree with each other? And do you have some sort of hierarchy for deciding which sensors are true or which sensors are more reliable? Just for context, on our PL side, we often have the capacitance and the density tool not agreeing. And one example was we were having water droplets with sand entrained on them, resting on the plate. So I'm just wondering if you have any examples like that for the fast tool.
Yeah, we do. Bon, not always an example we can share maybe openly and on records, but so for instance, in oil emulsion, that's why also we develop the new capacitance. We can see that if we are looking at oil emulsion or high gas rate, we can see that the capacitance tend to perform better for measuring water holdup than the conductivity probes when you have a really small water droplets. So in terms of hierarchy, it will depend on the. You can see that when you are logging, I would say from bottom to top, and when you see increase of speed from with using the spinner, you can see at some point that, for instance, conductivity will stop measuring water holdup. So the water holdup will be too small, and then you see disconnection of the water holdup not agreeing anymore between measurements. So there are things we recognize when we look at all the data, namely velocity versus water holdup. So I must say that the optical probes that was shown by Abdullah, our optical probe are triphasic. They generally have water holdup that are reliable quite a long time when velocity are increasing. And that's why we offer different type of physics depending on your environments. So it's important when the likes of Abdullah and the operator are sitting together that the understanding what's going to be the flow regime. And I would say also when you want to use a Doppler, Doppler we have are ultrasonic, so they will work more when liquid phase is dominant. But if we are the setup also will depend whether you are looking at very low flow or more higher flow. So that's important conversation to have during the planning.
Yeah, so that's what I was getting at. The planning is probably a very critical phase for you guys. Is it that you can select and choose these sensors, or are they all built into the tool? So you're getting this data regardless.
Well, I think it depends how many seats you have. So when you have a fast V4 or an axial fast, the sense has a lot of slots for measurements. So sometimes it's possible that in a location you will have will put different type of physics, and you have enough. You can live with the configuration for a different type of environment. So that's possible. It all depends what is what are the level of azimuthal resolution and senses. For instance, V4 has 16 array probes. So when we are in a well where we don't need, I would say all the time 45-degree resolution, but you want to do triphasic evaluation, a single tool will be equipped with different types of holdups and can be used for different type of environments. Yeah. So I think the axial has quite a lot of measurement that can be put in. So it really depends what type of deviation, what is the ID of your well. But generally it works quite well that we have the time to change the probes to fit the survey. And people like some service companies that OpenField trained, they are the level of Oilserv. Oilserv is a very old customer from OpenField. So they are able to change, they are fully independent in terms of changing probes. They are not the only one worldwide, but there are not so many service companies who have the level of expertise with fast tools, OpenField technologies.
Okay, thanks so much. That answers my question.
You're welcome, Stephen. Feel free to reach out.
Mr. Abbas, Petrophysics Manager with the CNOC, he have some question.
Yes.
Mr. Abbas.
Hello, Mr. Mazin. Thank you, Mr. Abdullah. Just
Hi.
I have small question about case number 1. If you
Yes.
go back, case number 1,
Okay.
the slide.
Okay, so
The
this
result.
is the one. The result, yeah?
Yes, another slide. Yes, this.
right.
I see this is 1 reservoir or 2 reservoir?
It
This
is,
case.
all right, so this is
If one reservoir,
it is,
if one reservoir, how upper part is water and lower part
all
is oil?
right,
It's the
you
same.
are right.
You have
It's
some
good
water
question.
injection.
This is good question. So this is a fractured reservoir. Okay, it is not matrix. They are producing from fractures. And you know, with fracture reservoir, you cannot expect where the water entry will be. It can be in the bottom, from bottom, it can be from the top. It depends on the fracture connectivity, okay? So yes, this water production from the top, it looks like it's coming from a fracture, okay? That's bring this water into this compartment, which is isolated between two backers, at the top and the bottom, the top above and below the top SSD. Yeah.
Even you have fracture, but for example, if have edge water, you should all flood it. If have edge water. If have water injection with vertical fracture, maybe happy like this.
Yeah, so it depends on the fracture system. If the fracture is connected to the water zone, then this fracture will produce water. Okay. If you don't have fracture connected to the water zone across the bottom, there will be no water. Yeah. So it depends on the fracture system.
In our field, happen like this, but our case different. We have water injection with vertical permeability. Happen like this.
All right. So you are injecting water. You are injecting water in a fractured reservoir, right?
Not a fractured reservoir, but we have K vertical, high K vertical. We inject in bottom in water injection well, but I see the water on the top of another production well.
Okay, yeah. So yeah, whenever you have injection, then here in this one there is no injection of water. Huh? It's aquifer water. God knows coming from where, but they are injecting gas in this one and in this field. It is the same field where we have this example. With the gas high gas oil ratio, this gas is produced gas, is injected gas. They are injecting gas and it's coming from the top. And we have seen, because it's fractured reservoir, we have seen many cases in this field that the gas entry is coming from the bottom, although they are injecting at the top. So there is a fracture that brings the injected gas all the way to the bottom and getting into the wellbore across the bottom SSD. So with fracture system, you cannot expect the entry point. Same way, you cannot have geothermal. I have seen a question about the temperature profile. Same thing with the mixture, with the fractured reservoir. Joule-Thomson effect cannot be behaving normally because you might have water entry from shallower than the produced interval or the inflow interval, or deeper, that will affect the Joule-Thomson. Yeah.
Thank you very much. Thank you.
No problems here.
If there is no more question, okay, just maybe I will have a last question. for closing. I know the answer, but maybe some audience will be interested.
Good,
So
good.
the
For other
optical-
people to know.
Yes, maybe other people interested to know.
Yeah.
So this optical tool is only for gas detection, or it is a three-phase tool? Like it is similar to other optical, or it is more advanced version of the optical we saw from other competitors?
Yeah, so thanks for asking. So actually, when we have when we sell, it's we call it the triphasic. We sell it. It's triphasic optical probe because it has a very wide range of measurement in terms of. So it's like a 64-bit electronics. So we have and we have the same gate when we don't change the measurement gate when we are measuring this actually voltage. It's a photoelectric measurement that come back. And the signal for optic gas, I would say clean on the clean probe is just to give in terms of range 32 over 30,000 raw count, optical counts. For oil, it can be very low, 1 or 2,000. So it's important to say we have we have very fine dynamic range, and at each acquisition time, the sampling, digital sampling is around 30 kilohertz, 30 kilohertz. So we have a lot of data sample per acquisition rate that can be 4 hertz, 8 hertz. And we are measuring not just the calculated gas holdup or oil holdup by the firmware. We're storing the raw data, minimum, maximum, average of the optical, counting bubble count. So basically you can want people to QC the data, but also able to reprocess the data. And we notice even when we have three-phase present, that we can get three-phase hold up. This case is when we are water dominant, so when we really do this reprocessing. But yes, thanks for asking. That's important to say. We have a fix. We don't change anything. We have fixed acquisition, and we have the same level of resolution, whether we have only gas present, or gas and oil, or gas, oil, and water. There's no automatic gain control because we have the very new electronics. We are able to have this fine resolution optics. I must say there is one case that we cannot discriminate oil versus water. When oil is very light and water is very saline, the refractive index of both are very close. So that's down to the physics. In that case, we cannot discriminate oil versus water. Yeah.
Okay, thank you, Virginia.
Welcome.
And I believe we will conclude this advanced topic webinar. I hope the attendees have get benefit from it. Okay, it will be recorded in all cases and will be put on YouTube and LinkedIn channel. I'd like to thank Abdullah as well for his contribution for this
Thank you.
Case study, very good.
Yes,
Yeah.
thank you so much. Last word from Dr. Mohammed before we close.
Okay, thank you, Mr. Mazen. I would like to thank Ms. Virginie Schoepf, a senior petrophysicist at OpenField Technology. Also, I'd like to thank Mr. Abdullah Manea, a wireline domain champion with Oilserv, about the informative presentation, and we would like to continue with you, certainly, and see you at future events. Also, I would like our attendees, Iraq chapter SPWLA, for their attending today with the 5th webinar, and hope to see you again in the other webinars. Thank you.
Thank you very much. It was a pleasure.
Yeah,
Thank you very much, Mr. Mohammed and Mr. Mazen. Thank you, everybody. Thank you, Virginie.
Thank you.
Yeah,
thank you.
Thanks for all attendees. Okay.
Yeah.
Have a great day.
Bye-bye.
Goodbye.
We will follow you on next meeting. Cheers, bye.
Inshallah.
Inshallah.